Okay, I think we're rolling. So last time we left off here where we were talking about we just got to the point where we're going to start talking about writes to the cache. So far, we've only talked about reads. I went back and looked at your quizzes, and most everyone got um, the question about the different types of cache misses correctly. So that's good. The only comment, one of the comments I had is when I asked you to define the index, the tag, and the valid bit. A lot of folks defined them very specific to the example that we gave, and said, the index is 3 bits and the tag is 2 bits, and that was fine for that particular example. But what I wanted to point out is the fact that those parameters change as those bit widths change as your cache parameters change. Okay, so really, I was looking for a more generic answer. The index in a direct map cache is log 2 of n, where n is the number of cache lines you have in the cache. So the index uniquely identifies exactly what location every block in memory must be mapped to inside that direct map cache. Okay, and we can see from this diagram, in this particular case, the index is 8 bits because we have 256 cache entries, or cache lines, or cache blocks, however you want to call it. Um, so that's the main thing I wanted to point out. And then the tag is whatever's left over in the address. So if it's a 32-bit address and 2 bytes are out, or 2 bits are allocated to the byte offset, and in this particular example, the cache block contains 16 words, okay, 32-bit words. Then we have um, 4 bits allocated to the block offset, okay, which identifies which particular word we're requesting within a given cache block. And then 8 bits is allocated to the index because there's 256 cache blocks. And then the remainder, which in this particular case happens to be 18 bits, is left to the tag. And then we have the valid bit, which indicates whether the block in the cache is valid or not. Now, of course, as we continue down our journey of memory hierarchy, we're actually gonna talk about some other bits. In fact, we should talk about an additional bit that we have to add to each block today, and that's to help us out with writes. Um, and specifically, that bit is called the dirty bit. And then, depending on how the remainder of the semester goes, if we get to the point where we're talking about shared memory, that adds an additional um, state that needs to be added to each block. And specifically there, for each block in the cache, we keep track of whether that block is being shared by other processors, or whether our particular processor has exclusive write access, or whether we have exclusive read access, so on and so forth. And so there's a little bit more state that has to be maintained when we share memory. And because we use these caches to share memory amongst multiple processors, that memory sharing scheme is at a cache block granularity. Okay, so far we've talked about 3 cache misses. We have compulsory misses, which are the initial misses that are due to an empty cache. We have the conflict misses, which are due to our rigid block placement strategy. As we increase the amount of associativity we have in our cache, we decrease the likelihood of conflict misses. And of course, fully associative caches have no conflict misses. And then capacity misses are due to the fact that our cache just isn't large enough. It turns out a fully associative cache can only have compulsory and capacity misses amongst these 3. Okay, well, just getting a little ahead of myself, but when we start talking about shared memory, there is a 4th C that we add to this list, and that's a coherency miss. And that has to do with when a processor writes to a particular shared copy of data, then what all the other processors do that are sharing that particular block, cache block, what they do is they actually go and invalidate all of the cache line. They invalidate it. Okay, and so let's say processor A, B, and C are all sharing a particular block of memory. Okay, a particular cache block. If A goes ahead and writes to that particular block, then A sends out a message. Okay, actually before A even writes to the message, sends out, or before A even writes to the block, A sends out a message to all the other processors out on the bus that says, "Hey, I want to write to this particular block of memory." So then what every processor does is they look inside their cache to see if they have that that particular block inside their cache, and if they do, they invalidate it. Okay. So what that does is that instantly allows a processor to gain exclusive access to a particular block of memory. Okay. So all the other processors that were sharing that block now are no longer sharing it because they invalidated their entry. And then processor A can go ahead and write to that block of memory, okay, and then the other processors, when they want to again read from that block of memory, they actually have to get the most updated copy from processor A. And that's really getting ahead of ourselves. So if that's confusing, don't worry. We're going to talk in depth about that in later lectures, but I just wanted to kind of give you a vague idea of how we actually share memory using cache. And of course it's usually the last level cache where memory is shared. So like in the i7, it has 3 levels of cache, and it's that third level of cache that's shared amongst all the processors. So each processor has its own private level 1 and level 2 caches, and then there's a shared level 3. And of course, what's neat is as a computer architect, you can architect that memory hierarchy however you'd like. There's a lot of knobs to turn when it comes to memory hierarchy, and we're going to talk about a couple more knobs today, okay, specifically having to do with write. But with all these knobs to turn, you have plenty of options, and for example, you might actually choose to share. Say, for example, you might choose to have 4 processors share a level 2 cache, and so then each of this cluster of 4 processors has private level 1 and then shared level 2 amongst the 4 processors. Then you might have 4 clusters of these 4 processors, in which case the clusters share at the level 3. So each cluster has its own private, or well, it's semi-private at that point, level 2. Okay, and in fact here I should be drawing this. Okay, I realize I'm really getting ahead of myself. Okay, but in this case, let's just say 2 processors share a level 2. Okay, so we do this, and then let's say they share, these 2 processors, okay, share a level 2, and then I'm going to go ahead and, boy, I didn't give myself any room to do this, did I? Okay, here. Unfortunately, I got to redraw this. Okay. That's the downside. Well, I should be able to just pick that whole mess up that I drew and move it somewhere. But anyway, so we're going to have, we have 2, I'm just going to do 2 processors, okay, for ease of explanation here, and then we got a bus between them, and each of these connect to our bus, and that's a level 2. And then we're going to basically duplicate that. We've got another cluster of processors. Okay. Okay. We do that, and then they're going to share this level 2, and then we're going to go ahead and do this. Now, the the thing about this architecture is we'll talk about when we get to memory hierarchy is that, and this is the level 3, as we get to sharing the memory hierarchy, we're going to talk about is we actually try to divorce ourselves from a bus-based architecture. So, um, and so because there's a lot of limitations, performance limitations when it comes to a bus-based architecture. Buses don't scale well to a large number of cores. Um, I need to take a break because I do not get the usual feedback in my ears that indicate that I'm actually recording, and I would hate to go on rambling for an hour and 15 minutes to myself and then find out I'm not recording. Okay, turns out we were recording, so we're good to go. All right. So what we have here is two clusters of two processors that are sharing memory at different levels, and so we can do that. And as I'll talk about when we talk about memory hierarchy, sharing within the memory hierarchy in depth later, is that we try to divorce ourselves away from a bus because the bus becomes a bottleneck as we scale out to more cores. So a better way of stating it is that a bus-based architecture does not scale very well. Okay, and we try to utilize like mesh networks and other like ring networks and so and often they'll have a series of buses where one's high performance and allows you to go um, across the chip from one core across to another core across the chip, and then other buses allow you to communicate with nearest neighbors. So there's all kinds of different options we have there when it comes to architecting our memory hierarchy when in the presence of multi-core. So anyway, again, I'm getting quite a bit ahead of myself. So okay, so that was be a fourth type of cache miss. Okay. Um, yeah. Other than that, everyone seemed to do very well on the quiz, so I'm pleased. You all seem to be understanding what I'm talking about here. So memory hierarchy is a really fun topic, um, and and it kind of answers some of the questions you may have had when specking out a computer system and whatnot. So. Okay, so up to this point, we've kept it simple, and we've talked about reads and how we respond to read requests. But the next question is, what do we do when we actually want to write? Okay, to a piece of data. Okay, so if we have now, obviously our instruction cache doesn't write. Okay, the instruction cache is read only, so that's why the instruction cache. I actually had a lab um, in previous semesters where they developed an instruction cache because it's read only. Now it has its own challenges, especially if you're designing a cache for an x86 processor, as we talked about when we reviewed those papers. And we're going to go back to those papers, by the way, once we get a little more memory hierarchy under our belt, and so we can then better appreciate that. So instruction caches have their own challenges because because they're intermingling with the fetch and decode stages of our processor. More advanced processors will actually pre-decode as they bring data into the instruction cache, and actually data in the instruction cache is sometimes um, stored partially decoded rather than in the like for a RISC instruction, or rather than it being a 32-bit instruction that you fetch from memory, it actually may be a partially decoded instruction, and so there's all kinds of tricks you can play there, and of course x86 definitely does a lot of pre-decoding of their complicated instructions, and so the instruction cache actually stores um, partially decoded instructions. Now, of course, we didn't see that in the 486 and Pentium. Those more advanced techniques came later, especially when they started introducing what they referred to as the net burst architecture, which was the Pentium 4. That thing was a beast. Anyway, so instruction caches have their own challenges, but data caches they have the big challenge of having to handle writes. Okay. So there's two different strategies for writes. The first one is write through, which basically means when you write to your level 1 data cache, okay, then that write is immediately forwarded to the next level of memory. So if you have a system that only has a single level of cache, then that would be the DRAM. So when you write to your data cache, those writes are also forwarded to the DRAM. And the idea with a write through cache is that writes don't have to actually block the pipeline. So reads do, right? Because correct instead of I have to be careful about using the word write. Um, so reads block the processor, and the reason for that is when you're loading data from a data cache, um, that that data is satisfying dependencies for that instruction stream. And in an in-order pipeline processor, um, you have to basically stall the whole pipeline that until that read is satisfied from the memory system. So if the um, data cache encounters a miss, okay, then an in-order pipeline stalls. The whole pipeline stalls at that point. You can allow write back to happen, but essentially the majority of the pipeline comes to a grinding halt uh, when you encounter a cache miss. Okay, but in the case of a write, when you're writing to the next level of memory, you don't necessarily have to stall the processor, okay, for that write. Okay, so you can send that request off to the next level of memory and then continue on with your instruction processing. Now, if you follow it up immediately with another write, then you will probably have to block your processor, unless you have a place to put these writes, and we'll talk about that in a minute. Okay, so that's write through, and the big advantage of write through is it's just super simple. Okay. Anytime you write to your data cache, you forward the write to the next level of memory. Okay. The next strategy is write back, and write back essentially only writes back the data when that particular block is being evicted. Okay. So this is where this dirty bit comes in. So what we do is we we maintain an additional bit of state in our cache for every block, and so when we initially pull a block in, we set the dirty bit to 0, indicating it has not been modified. And then when we write to a particular word within that block, or actually writes in a 32-bit MIPS processor, you can actually do byte writes. So even if we write to just a single byte in our block, then what we do is we mark that entire block as dirty. Okay. Now there are some optimizations that we can do on top of that, and so one optimization is rather than keeping a dirty bit for the entire block, let's keep a dirty bit for every byte. But you can imagine the overhead that's associated with that, right? You would need for a 64 byte block, you would need 64 bits just to maintain that. So you may choose to do it at the word level, or you may just choose to do it at the block level. Okay. So if any byte in that block is modified, then you mark the entire cache block as dirty. And there's advantages and disadvantages to that. But anyway, that's getting ahead of ourselves. So let's just say we use 1 bit per cache block. So anytime that a portion of that cache block is modified, then we mark the dirty bit. Then what happens is if we keep reading and writing to that cache block, nothing happens until we go to request a block of memory that um, that aliases with that particular dirty block. Okay. So in other words, what we're going to encounter is a conflict, and we're going to evict that dirty block. Okay. So if the block is dirty, then there's one additional step we have to do in the write back write back strategy, and that's to basically write that block back to the next level of memory. Okay. Now, if we're evicting a particular block and the dirty bit is not set, that means that we never wrote to it. So the most recent copy of that block is actually in fact in memory. Okay. And so in that case, we don't actually write it back. We don't need to. Okay. But if we're evicting a block and its dirty bit is set, okay, then that means that the most recent copy of that block is actually in our local cache, and so then we need to go ahead and write it out to the next level of our memory hierarchy to keep our memory hierarchy consistent and coherent. Okay, so that's write through and write back. So write through, just it's a simple process. Anytime we write to the cache, we immediately forward that to the next level of memory. And we will do so at probably the word level or byte level, depending on our bus and everything. And so if we modify just a byte, we'll write that back. If we modify a word, we'll write that back. And of course, we can't modify at any given time more than a word. But then write back, on the other hand, defers the writing to when the block is being evicted. So the advantage of write-through, we said, is simplicity. The advantage of write-back is it significantly reduces the amount of traffic that we place on the bus for the next level of our memory hierarchy. So in write-through, every little write goes all the way to the next level of memory, which adds additional pressure on that bus and that memory system. If it's if we only have one level of cache, we're going to keep that DRAM controller busy, continually writing data back to DRAM. So, but in the case of write back, we only write back when we modify a block. Okay. Now, the disadvantage of write back is it unless we buffer that block, it actually increases our penalty for a cache miss, because with write through we write it back to the next level of memory, so we never have this concept of a dirty block, and so when we need to evict a block, we just simply overwrite it because we already sent all the modifications to the next level of memory. Okay. If in the case of write back, however, we now have an additional step that we have to carry out, and that's to write the block back to the next level of memory if it was in fact dirty. Okay. So they have their advantages and disadvantages, and there's also an advantage with write through when it comes to cache coherency schemes and sharing memory. Okay. It's we don't have to have that invalidation process I was talking about if we use write through. Okay. So what's interesting is we actually use different strategies at different levels of memory, and again, this is all up to you as the computer architect. So even though computer architecture may not be advancing as much as it used to in the glory years, there's still a lot of engineering to do, okay, when it comes to architecting, especially at the memory hierarchy level. So you could purchase a core from ARM and then architect the higher level memory hierarchy, okay? And so there's still a lot of decisions you can make, whether you do write through and write back. The other thing is some caches are very advanced, and they allow the write strategy to be actually programmed and configured dynamically. So when the processor comes up, it can configure it, or the operating system can even reconfigure it. Okay. Well, in either case, we can actually improve the performance of our memory hierarchy with a write buffer. Okay. So whether we're using write through or write back, we can add a buffer that just simply buffers our writes. Okay. And it sits between us and the next level of memory. So let's go ahead and let's take a look and see what that would look like. By the way, I used to go and insert blank pages in the lecture slides, and that I found was a real problem, especially when I go and find a mistake and modify it, and I have to overwrite the whole thing. So I was spending a lot of time inserting blank pages, and finally I'm like, okay, I'm just going to create an entire presentation of blank pages, and then I'll just go ahead and use those as my virtual whiteboard. Okay, so what does this look like? So we're going to go back to a single core architecture. Boy, that is not a straight line at all. Okay, there we go. It's a little bit better. So here's our instruction cache and our data cache. And our data cache is, of course, the one we're actually interested in here in this discussion. And let's just for now, assume that we have just one level of cache, so then this is our memory. Okay, and then we're going to have a bus here, where it goes to that bus, and then our iCache and data cache connect to that. Okay, this is what it looks like without a buffer. Write buffer. Now I'm gonna redraw these arrows to be a little more specific. We're just gonna say that this is the direction of data flow, not including the address and other signals that are required for this bus. This is just data. So here we see the instruction cache doesn't write data, so the arrow is only one direction. The data cache reads and writes, so it's both directions. Okay. All right, and then we need that so we can differentiate. So what we're going to do is we're actually going to stick a write buffer here. So we're just going to put a buffer here. Okay. And we're going to show that writes go through like this. Okay. So this is our write buffer. We'll label that. Again, this write buffer works well for both strategies, whether it be write through or write back. Oh, by the way, quiz time. Define write through and write backs. Define each of those strategies. Okay, that's your first quiz question. Okay. All right, so this is our write buffer. So what we do is when we encounter a write, okay, whether let's talk about it in the write buffer in the context of write through. Okay, so this write buffer drastically improves the performance of write through. Because as I mentioned in write through, if you write once to the cache, then it can go ahead and forward that write to the next level of memory. But then if you write again, it has to have somewhere to put that write. If it doesn't have anywhere to put that write, then the processor has to stall. And so if your writes consume, I don't know, let's just say 10% of your instruction stream, you can imagine that you can very quickly stall your processor because of having nowhere to put those writes with write through. So write through is almost always used with a write buffer. Almost always. I don't even know if write through really works well without a buffer. So then your buffer, let's just say it's 4 or 5 entries deep. Then what happens is when you write to the cache, the write goes into the write buffer. And then when you write to the cache again, that write goes into the write buffer. And so every time you write to the cache, that write is forwarded into the write buffer. And then what the write buffer does is whenever there's extra room on the bus, whenever the bus is not busy satisfying an instruction cache access or a data read, then the write buffer grabs a hold of the bus and sends that data to the next level of your memory hierarchy. Okay, so the write buffer allows you to prioritize reads over writes, and which because the reads are what will stall your processor, but the writes won't as long as the write buffer doesn't fill up. Now, once the write buffer is filled, okay, then the processor has to stall because there's nowhere to put additional writes. Okay, so So with a write buffer, you can prioritize reads over writes until your write buffer fills up. And then when your write buffer fills up, then you have to prioritize the write buffer, otherwise your processor gets put into kind of a deadlock position. But the point is that the write buffer provides a place to store those writes and allows the processor to continue making forward progress. Okay, if you didn't have the write buffer on a write through, then you would basically have to stall on back-to-back stores. Okay. Now the thing you have to keep in mind is that access to the next level of memory will take you know, tens of clock cycles. Okay. So it could take anywhere from 5 to 20 cycles depending on how your memory hierarchy is designed. So a write takes about 5 to 10 clock cycles, right? And this is a RISC processor that theoretically could issue a write on every clock cycle. Now, luckily, program statistics tell us that store words are not all that frequent, right? Loads can account for like 20 to 30% of your instruction stream, and store is like 10 to 20%, kind of general rules of thumb. So the idea is that your write buffer has to be sized accordingly so that when you have bursts of writes, you don't end up stalling the processor. But ultimately, if your next level up memory does not have enough bandwidth, then with a write-through strategy, if you have enough store words, if enough store words are a significant percentage of your instruction stream, you're inevitably going to start stalling the processor. It's just the way it is. So that's why write back tends to be preferred, but there are a lot of advantages, and write-through is still used fairly often. So let's talk about the write buffer now in the context of the write back. So how does the write buffer in the write back policy, how does the write buffer benefit the write back strategy? Well, if you remember, one of the downsides to the write back strategy is that when you have a cache block that you're evicting, the first thing you have to do is write that back to the next level of memory before you can pull in another the new cache block. Okay, that is unless you have a write buffer. So you can even have just a single entry write buffer, and with a write back strategy, when you encounter a cache miss, then you just push that evicted block to your write buffer, and then you can begin reading that next cache line that your processor requested. And again, this is a case where you would also strategize or prioritize cache reads over writes. So again, the write buffer would have kind of the lowest priority amongst the instruction cache and data cache reads until, of course, the write buffer fills up. But then you can then allow a read to happen before the write happens. So that allows you to reduce your miss penalty significantly when it comes to a write back scheme. Okay. So that's a huge benefit for the write buffer in the case of the write back strategy. Okay. Okay. So let's just recap about write through. The advantage is it's simple. It keeps the next level of memory consistent. That has to do with sharing memory. Disadvantage, a major performance bottleneck because the processor must stall on multiple writes and creates congestion on the bus in the next level of memory. Okay. Write back, the advantage, much better for performance as writes do not go to the next level as a block is being evicted. Okay, rather, much better for performance as writes do not go to the next level until the block is being evicted. So if we have repeated writes to the same data, okay, you can see how write back can quickly become advantageous. Okay, because those multiple writes don't actually ever um, get pushed up to the next level of memory. Um, they they can repeatedly happen and and actually just happen locally, and then once we then move on to a different cache block, and that cache block that we were writing to needs to get evicted, only then um, does that modification get pushed to the next level. So it significantly reduces the pressure on the bus and the next level of memory. Okay. The disadvantage is it makes the cache controller more complex, especially when we're talking about sharing memory. Okay, so maintaining consistency with the next level of memory is a lot more complex. And even there's consistency between the instruction cache and the data cache. If your processor is actually moving data into a particular region of memory, that data is instructions that you're going to execute later, because it's kind of a von Neumann architecture. This modified Harvard architecture has to be very careful about that, because when you move data, you move it through the data cache, but because we're using a write back strategy, that data doesn't necessarily make it back to the memory. Okay, and then we go and start fetching from that region of memory with our cache, and that data hasn't yet made it up to the next level of memory. Well, what do we do? Okay, and so the cache, in the case of a write back strategy, there has to be a mechanism that allows the processor to force write backs to happen. Okay, so if the data that you're moving happens to be instructions, then before you kick off the execution of those instructions that you moved, you have to force that write back. Okay, and so there, in the MIPS ISA, there's a cache instruction that allows you to force write backs. Okay, that cache instruction is very powerful. It's really the only instruction that MIPS uses for maintaining caches, but it has a lot of different things it can do. It can invalidate cache lines, it can force write backs, it can change the write strategies. There's all kinds of things it can. Okay, we talked about the write buffer. Okay, and so we'll just go and review that real quick. In the case of write through, it avoids stalling the processor. As long as the write buffer is not full, and once the write buffer fills up, then we have to stall the processor. And then in the case of write back, it allows the retrieval of a new cache line to happen before we actually write that cache block back to the next level of memory. And so we can prioritize reads over writes. The other thing we can do with a write buffer is we can combine various writes and memory locations. We can pack them into co-located data. We can pack into fewer write transactions. So there's some advanced functionality that a write buffer can provide, and can overall make the writing of data back up to the next level of memory much more efficient. Okay, so there's a lot of things that a write buffer can provide. So okay, well, so we talked about write through and write back, and then there's this concept of write allocate and no write allocate. And really what these two strategies define is what the cache does in the case of a write to a block of memory that is not already in the cache. Okay, so up to this point, our examples have included writing to blocks that we've already read first. So if you think about it, let's say we're talking about a write back strategy. We read from a particular block of memory. The cache controller goes, or our cache looks in its data store and finds that the block is not actually in memory or in the cache. Then it goes to the next level of memory and retrieves it, brings it in, and now it's resident in our cache. And then at some point while we're accessing it, we decide to write to it. Okay, then we go ahead and modify the dirty bit from a 0 to a 1, and so on and so forth. But what happens if we never read the block first? Okay, so we go and write to a particular block of memory without reading from it first. Okay, then the question is what do we do? Do we, in the case of a write back cache, do we go ahead um, and pull that block of that cache block in to our cache, and of course potentially evict another block, okay, and then go ahead and modify it, okay? Or do we just say, well, it's not in the cache, we're not reading it, so we're just going to go ahead and forward that write out to the next level of memory without actually bringing that cache block in, and we only bring it in once it's actually read um, from. So write allocate is the strategy where if we write to a block, okay, in the case of write back, without first reading it, then what we'll actually do is we'll treat it like a read miss and bring that block into the cache and then modify it. Okay, that's write allocate. Okay, um, no write allocate is where we actually if the cache block is not in the cache when we write to it, then we just forward those writes up to the next level of memory, okay, which of course we more than likely have a write buffer, so they actually just go into the write buffer, okay, and then we don't actually um, bring that cache block into the cache until it's actually read from, okay. So um, we can actually use this technique for write back, but in the case of write through, well, write through sort of always just follows the policy of no write allocate, right? So it always, if you write to it, it forwards it to the next level of memory. It doesn't matter whether the cache block is in the cache or not, right? Okay. And again, this strategy works well with a write buffer. And one thing you might be asking yourself is, well, why does it even matter? Okay, so how do these different strategies optimize program execution? Well, if you think about it, oftentimes when we process data, you might have a situation where you never actually read the data and you're just always writing. So think about taking two arrays and adding them together and writing the result in a third array. Okay. Well, in that scenario, you're going to read in the two arrays and perform a computation on the elements within that array. But then for the third array, you're just always writing the data and you never read it. Well, it doesn't make any sense to then read that data into the cache, which forces you to, by the way, evict other cache blocks that are actually being used to bring in data that you're only going to write out once and never read again. Okay, so in that particular case, no write allocate actually makes a lot of sense. Okay, and so no write allocate is actually a pretty popular strategy. Okay, and there are a couple other strategies that we talk about in the graduate class that have very subtle nuances between the two. But anyway, that's write allocate and no write allocate. Okay. And again, a lot of cache controllers allow you to program this on the fly, so you can actually adjust the caching strategies based on your particular program needs. Okay. And of course, there's a lot of ongoing research on actually having those strategies adjust dynamically, so they kind of see the needs of your program and adjust accordingly. So okay, so now that we've talked about different write strategies, and we talked about how to actually bring data into the cache. Now we want to talk about how performance is impacted based on the memory hierarchy. And of course, this leads us into homework problems. I haven't released your third homework yet, but I plan to do so in a couple of days, and you'll basically have till well, there's not that much time left in the semester, so you'll probably have about 10 days to do that homework, and then as soon as that homework is due, we'll have I'll give you the exam. Um, and so that'll be the final exam. And the final exam, of course, will be take home, and you'll have a couple days to do it. I was able to give you a week to do the last midterm exam, but on the final exam, uh, we're just not going to have a lot of time to do it. Um, so anyway, I'll have to strategize how we do that. But basically, I think I'm going to have the final exam due also on the 16th of May, which is the last day, official day of the semester. Okay, that pushes out the semester as late as possible. So anyway, and I'll probably have to trim back homework 3 from what I've done in the past. So I won't make it as long as I've done in the past, just because, I mean, let's be realistic. This pandemic has affected a lot of us, and it's just crazy for us to expect to get through as much material as I have in the past. Every year, I hope I become more efficient with the class, and get a little bit further in the material that I cover, and it really has more to do with not covering more material, but more efficiently covering the material, or not covering as much of the material that's less important. But then this thing kind of threw a wrench into the whole mix. But anyway, all right, I'm done with my saga. Okay, so with an in-order processor, looking at how the memory hierarchy impacts performance is actually quite simple. And it really has to do with the fact that an in-order processor, as soon as it encounters a cache miss, it really just stalls. Okay, so no forward progress is made during a cache miss. Okay, so we can account for that in our calculation of CPU time. So um, our really our CPU time, the amount of time that we actually spend executing a program, is now the CPU execution cycles, which you all already spent time in your prior homeworks calculating, plus now the memory stalls. So now the stalls due to accessing the cache. Specifically refilling the cache. And then, of course, that gives you the number of cycles, and then you multiply that by the cycle time, and you get your execution time. So in the case of a hit, okay, with an in-order processor, we assume there's no interruption in instruction flow. So a lot of times I'll phrase this in a homework problem. I'll say assume a perfect memory hierarchy. And what I mean by assuming a perfect memory hierarchy is assume that every single cache access is a hit. Okay, so every single cache access is a hit, in which case we would our analysis would look very similar to the analysis we did in homeworks 1 and 2, um, where where we didn't even account for any stalls due to the memory system. We just always assumed that the instruction memory and data memory were capable of delivering. Okay. Well, now we're taking off the rose-colored glasses when it comes to memory hierarchy and saying, well, there are going to be times that um, that the processor has to stall because the data is not in the cache. Okay, and of course the cache that directly impacts the processor performance is the level 1 cache. Okay, and so if we continue to hit in the level 1 cache, then we have no interruption in an instruction flow due to the memory hierarchy. Now, we're still going to have data hazards and control hazards and all of that fun stuff. Okay, um, so so really the memory stall cycles are due to our cache misses. Okay, so in terms of the miss rate, remember the miss rate is the percentage of accesses to our cache that actually miss. So the percentages of all of the accesses that are misses. Okay, that's our miss rate. So miss rate is basically number of misses divided by number of total accesses. Okay. Well, if we take the miss rate, okay, and we multiply it by the miss penalty, okay, then now we have an idea of how much time um, we actually spend. Well, okay, I'm sorry, I missed a major component. If we take the number of memory accesses per program times the miss rate, that right there gives us the number of total misses that our program encounters. And if we take that and multiply it by the miss penalty, okay, which is the cost to go out and retrieve data in the case of a miss, now we have the number of memory stalls. Okay, the number of cycles due to memory stall cycles. Okay, different ways of saying that, but okay, and and we can also rephrase this in terms of the number of misses per instruction. Okay, so if we take number of instructions per program, multiply it by the misses per instruction, which is another metric we like to use. Typically, it's actually misses per 1,000 instructions because misses on a well-designed memory hierarchy happen fairly infrequently. Okay, then times the miss penalty. Okay, that gives us memory stalls per instruction. Okay, that equation really needs to be modified. I need to fix that. That's so we have memory stall cycles. It's really memory stalls per. Well, no, it's calculating the same thing. Um, the total number of memory stalls in a given program, but it's using this different metric. Okay, so sometimes we report in miss rate, and sometimes we report in misses per instruction. Okay, which is a percentage. Um, and I think I was getting it mixed up with branch prediction, where I was saying misses per kill instruction. Branch prediction, we use misses per kill instruction, but now that I think about it, I don't know that I've seen misses per kill instruction for caches, because even though misses are fairly infrequent, they're still more frequent than a branch miss prediction, believe it or not. Okay. Anyway, all right, moving on. And now keep in mind, the other thing we have to keep in mind when we talk about um, these memory stalls is we have memory stalls that are due to the instruction cache and memory stalls that are due to the data cache. And both of those cause our processor to stall and interrupt instruction flow. So in your homework problems, you're going to see that I have you first. A lot of times I walk you through in steps, and I first have you account for the memory stalls due to the instruction cache, and I'll have you calculate the CPI. Okay, so what I'll do in the homework problem is I'll tell you, okay, assume an ideal memory hierarchy. The CPI, assuming an ideal memory hierarchy, is 1.2 cycles per instruction, for example. And in fact, if you remember in some of your problems in homework 1 and 2, 1.2 cycles per instruction was pretty typical for the homework problems that we solved. And that's a pretty typical number for a well-designed pipeline, especially a shallow pipeline like a 5-stage pipeline. As you go out to more stages, more aggressive super pipelining, you end up with the trade-off is you end up with a higher CPI, slightly higher. So I'll say, hey, assuming an ideal memory hierarchy, we have a CPI of 1.2. But then I give you a miss rate for your iCache, and I tell you what the miss penalty is. Then I tell you to calculate the new CPI given this new information here. So then what you'll do is you'll actually calculate the number of memory stalls, okay, due to an instruction cache access, and and then you'll calculate how the CPI affects that. And of course, what's interesting is memory accesses per program is essentially equivalent for an instruction cache. It's equivalent to the number of dynamic instructions executed, because essentially you access the number of times you access an instruction cache is really the amount of times you fetched. Okay. Now, for an x86 processor, that calculation would get a lot more complicated, which is why we only consider RISC processors. Okay. And so then what I'll do in your homework problem is so you'll calculate your new CPI accounting for instruction cache misses, and then I'll ask you to calculate. I'll give you a miss rate of the data cache. I'll give you the frequency of load and store instructions. Okay, and then I'll give you the miss penalty for the data cache, and then you have to account the um, for the memory stalls um, required for accessing the data cache. So then what you'll see is your CPI gradually goes up. It starts at 1.2 for ideal, and then it may go up to like 1.4, 1.6 because of the well, actually, honestly, the iCache is going to be less impactful, so it'd probably go up to maybe 1.2, I mean 1.3 for the iCache, or 1.4. I'm just making up numbers here. And then for the data cache, you may see it skyrocket up to 2 cycles per instruction. So it gets a little discouraging as we start going through those homework problems. Okay. And again, we can use these simple equations because the in-order processor has no option but to stall in the case of a cache miss. Okay. Okay. So um, we can we can also separate out reads and writes. So things get a little more interesting when we start doing that, because we actually have a write buffer. Okay. And so, oh, and I've got this messed up. I need to fix that. But Um, the read stalls are the number of reads per program, which I would give you a frequency of that. Like, I would say, hey, 30% of your instructions are loads. Loads read from memory, of course. Then I would give you a separate miss rate. I would give you the miss rate for reads, okay, and then you would multiply that by the miss penalty for reads, okay. And then likewise, your write stalls, if you have a write buffer, is the the amount of writes per program times the write miss rate times the write miss penalty. Okay. Um, Plus any additional stalls you might have due to the write buffer. Okay. So what uh, we'll talk about that a little bit more. Maybe I'll talk about it right before I introduce the homework. I want to go over it maybe again a little bit. Okay, so yeah, again, your homework 3 is going to have a lot of problems like that now include the memory hierarchy in your CPI calculations and everything. Okay, and then there's also average memory access time that we'll talk about in a little bit here. Okay. Now, what about out of order processors? So, what's interesting about out of order processors is one of the main reasons we started running instructions out of order was to try to hide the uh, uh, latency for accessing the level 1. Okay, so um, out of order processors started becoming a thing in really the early 90s, and I mean, actually, what's interesting, this is interesting. When we study out of order processors in 538, we actually study a technique that was developed in 1967 uh, by Robert Tomosulo. I kid you not. Out of order concept, running instructions out of order, was developed in the 60s. There were two techniques. Robert Tomosulo's technique came just after scoreboarding, and scoreboarding was designed by
by Cray Seymour. Okay, so and this was in the late '60s. Okay, but obviously these techniques were really only used by supercomputers. Okay, in fact, Cray Seymour is considered the father of modern supercomputers, and so he had developed one of the earliest techniques of out of order execution. Um, and and Robert Tomosula's algorithm, that's like the textbook out of order execution algorithm. So they were developed in the late '60s, but um, really they didn't make their way into commercial processors until the early '90s. And in the early '90s, they pretty much adopted those similar techniques. So um, but in the early '90s, caching had become a very popular thing. I mean, every processor out there was caching, and so what out of order execution provided was a way of actually hiding the latency for satisfying a cache miss at the level one. And so the other thing that started becoming more mainstream in the early '90s was second level caches. Okay? Started out on board but off chip. Okay, so you could have a level two cache, which was really actually what it was. Is that what was interesting is the cache controller was on chip, and then the cache array, the data array, the memory array was an off chip SRAM chip, and so a separate SRAM chip. But the cache controller was generally still on chip. Okay, and so with those kinds of features, you could have a level two cache, and so out of order execution kind of came to the rescue and allowed us to now hide our level one cache misses because, like I say, one of the biggest disadvantages of an in order processor is as soon as you encounter a cache miss, the whole execution comes to a grinding halt. But with an out of order processor, what it'll do is when it encounters a cache miss, it will continue to execute instructions that don't depend on that load. Now, of course, there's more than likely going to be a dependency chain, and so you know that dependency chain will eventually catch up to you, and you may end up having to stall the processor. But with any luck, before you have to start stalling the processor because of data dependencies, you'll finish satisfying that cache miss. And of course, you're able to do so because you have a level 2 cache. And so the access time to the level 2 cache is much smaller than the access time to DRAM. And so the idea is that with you can couple out of order execution with a level 2 cache, and that will allow you to pretty much hide all of your level 1 cache misses. Okay, and so well, okay, so that's a really nice feature, but what does that do in terms of our performance calculation, our simple performance calculations? Well, it completely throws them out the window. The fact of the matter is you have to understand data dependencies and everything that are going on inside your program to actually um, determine how a cache miss at the level 1 will affect, or at the level 2 will affect your overall execution time. It becomes way too complicated. Okay, and so really we can only use these simple equations for in-order processors. And they're mainly used for pedagogical purposes, just to kind of give you an idea of how memory stalls can affect performance of a processor. But once we go out of order, really the only way to determine the effects on performance of our memory hierarchy is to simulate, and we simulate benchmarks, of course. Okay. So we'll execute a given suite of benchmarks, and with our memory hierarchy, and then from there we can actually determine how much of our program stalls because of servicing cache misses. But yeah, good luck calculating that with an equation. Okay.
So because of out of order execution, we like equations. Okay, we like to quantitatively analyze things, and so we'd actually like another way of measuring the performance of our memory system, and that's where average memory access time comes in. And I'm also going to have a number of homework problems for you where you calculate average memory access time. Okay, and so average memory access time gives us an idea of um, on average, how many cycles does it take to access a given cache? Okay, and so average memory access time accounts for the hit time plus the time to refill the cache because of misses. So the time to refill the cache because of misses is very similar to it's actually identical to your memory stall cycles. Okay, and that's miss rate times miss penalty. Okay, so the frequency of your misses times your the amount of cycles you spend per miss gives you an average number of stall cycles per access of your cache. Okay, and so if things are done right, this miss rate times miss penalty should be a fraction of a cycle. Okay, and then your hit time, well, that's for a simple 5-stage pipeline processor like ours, that's really just one cycle. Okay. Now, if you pipeline the um, the level 1 cache, then your hit time, becomes a little more complicated. Is it one cycle because even though your throughput, because it's pipelined, your throughput is one memory access per cycle, or is it, like in the case of the R4000 where it breaks it up into the data access into two stages? Is your hit time 2? Now that gets a little more complicated, but I'm not. Your homework problems, you'll find I'll basically tell you what the hit time is, and tell you what the miss rate is and miss penalty. Okay. Okay. So moving right along, again, your homework will help you understand the number of memory stalls, and how that relates to CPI with an in-order processor, and then you'll also have to calculate average memory access time. So I'll go over that stuff just real briefly again before I release the next homework, or I'll release the homework and then I'll go over it again. But in the meantime, let's move on to back to theory, and let's talk about placement strategy. So we talked about the two opposite ends of the spectrum, where we have direct mapped, which is a very rigid placement strategy, but very simple to implement. Very easy cache to build, and every block in memory or the next level of cache maps exactly to one block in your cache. Okay, and that's where the term direct map comes from. And so we can use the index to figure out precisely where in the cache that data block should be. But then on the other end of the spectrum is fully associative. Okay, fully associative means that a memory block can actually be placed anywhere in the cache. Okay, so of course the advantage of fully associative is it's a much more flexible block placement strategy, so we can more effectively use the cache blocks in our cache. And of course, the downside though is the complexity. It turns out you have to have a comparator for every cache block in a fully associative cache, and that's because in a fully associative cache, there is no index. There's no index, and so the question is, between these two opposite ends of the spectrum, is there a middle ground? And of course, yes, there is. Okay, and that's where we get into what's called set associative. Okay, so that's our middle ground. The middle ground is set associative cache that has a fixed number of locations greater than one that a block can be placed in. Okay, So, for example, a two-way set associative cache provides two different ways within a set that a cache block can be placed. And I've got a graphic that explains this if it's not quite making sense. Um, Hopefully it'll illustrate this. Okay. So, for example, a two-way set associative cache with 8 blocks has 4 sets, each with 2 ways. And any given block in memory can map to either of those 2 ways. Okay, so it's time for a diagram. Here we go. This diagram, I really like this diagram because it shows all 3 of the placement strategies. We have the 2 opposite ends. Let's look at those. Direct map. We have a particular block, and it can only map to it can only be placed in one particular location. Okay, and then we have set associative. Okay. Oh, and by the way, if we look at that, our block number is essentially our index, right? So for an 8-entry cache, we have our index has to be 3 bits or 2 to the 8, so we can uniquely identify each of the blocks. See, and that's here. So we see that a given block can uh, can only be located in or a given block of memory can only be located in one block of our cache. Okay, and the fully associative, notice it has no index. There's no index here. Okay, because this block, for example, a block in memory. Whoops, I'm mixing up. That's our tag store. A block in memory can actually be located in any one of these cache blocks. Okay, and then the point in between, which is our set associative. So our index, we actually only need 2 bits of index to identify our 4 sets. Okay, so we got 4 sets here, 0 through 3. Each set has 2 ways, so 2 blocks. So 2 blocks per set. And a cache block a particular block in memory will map to a particular set in the cache, and within that set, it can be placed in one of 2 ways. This is two-way set associative. Okay, two-way. Now we can have 4-way, 8-way, okay, and so on and so forth. Okay, and so there's like a spectrum. Okay, a spectrum between direct map and fully associative. Okay. Okay. So each block has its own tag, and we'll go back to that diagram in just a second to illustrate that. The sets are selected with that index. You know, the way to look at a direct map is a direct map cache is almost like a special kind of set associative cache where there's only one way. It's a one-way set associative. Okay, so in that case, your number of blocks is equal to your number, or your number of sets is equal to your number of blocks, and so each index has to uniquely identify each set, which uniquely identifies each block. That's a direct map. But then as we increase the ways of our set associative cache, we start moving over towards the fully associative cache, and we start as we increase the number of ways within our sets, we start decreasing the number of sets if we keep the number of blocks that our cache holds constant. Okay, so hopefully this is making some sense. So adding more associativity reduces the size of the index and increases the size of the tag because it reduces the number of sets. So if we go back to this diagram, we notice that every block in 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 a direct map, set associative, and fully associative, every block is given its own tag. Okay, every cache block has its own tag. So we're not reducing the number of tags that we have. Okay, so it doesn't matter what scheme you're using, whether it be direct map, set associative and fully associative, each block has its own tag that it's paired with. And you can of course see the reason for it. In the case of the two-way set associative, you use the tag. Okay, so you use the index to determine what set that block could be in, right? So for example, if our address is such that the set is 0, then it can be one of these two cache blocks. Well, how do we determine which cache block has the data we want, if any? Well, it's with the tag, just like we did in the direct map case. And then if we slide all the way over to the fully associative side of things, there is no index because a cache block can go anywhere in our cache, and we 100% rely on the tag to tell us which block it is we're looking for. Okay. Okay. Here's another diagram in how the one way, which is essentially direct mapped, two way, four way, and eight way, which in this case for 8 entries is fully associative. How they are organized. So it's just seeing the data in a different way. Here we have right here we have essentially the number of sets. Okay, these are our sets. And so for a one-way or direct map, 8 entry cache, we have 8 sets. Okay, and so we have an index that's 3 bits. For the two-way set associative, we have 4 sets. So we take the number of our sets and divided them in half because each set now contains 2 blocks. Okay, so we have 4 sets. Okay, and just as I said earlier, each block still has its own tag. Okay, then we can go four-way set associative. Four-way set associative now means that each set has 4 blocks, and since our overall cache size is only 8 blocks, that leaves us 2 sets. Okay, so how many bits of index do we need for that? Ooh, quiz question. Um, for the diagram on slide 51, how many bits do we need for the four-way set associative cache? So rephrased in a more general way, if we have a cache with 8 entries, a four-way set associative cache with 8 blocks, how many bits do we need for our index? Okay, and so, well, the answer is, of course, 1 bit. We only need 1 bit because there's only 2 sets. Okay? Whereas for one-way set associative, we needed 3. For two-way, we needed 2. For for four-way, we needed 1. And now, all the way on the other end of the spectrum, a 8-way set associative you can look at as having only a single set. So how many bits do we need? Well, 0. We only need 0 because we only have 1 set. This is one big old set right here. And so a fully associative cache has no index. Okay. Well, now one of the questions you may or may not be asking yourself is how do we construct a set associative cache? So it turns out it's actually very easy. We can look at our direct map cache as a building block, okay, and from there we can build a set associative cache. So let's go to the next diagram here. Okay, so this is an example of a cache that has 256 sets. Okay, and it's four-way. Okay, and so if you look, each of these are basically like a single direct map cache. We feed it the index. The index looks up the particular block, and then we retrieve the tag. Okay. The difference is this is an 8-way set associative. Okay. So we have to have, a 4-way set associative. So we have to have 4 for comparators. Okay? So what we're going to do is we're going to take our index, which, because we have 256 sets, our index has to be it has to be 8 bits wide, because 2 to the 8 is 256. Okay, so we take the 8 bits and we feed that into each of these direct map caches, and they then retrieve the tag and valid bits, and then we then compare the tag and valid bits for each of the ways. And then the way it's designed is only one of these ways should actually hit. If two of them hit, all hell breaks loose. So we just ensure that that never happens. Don't put that has to do with your refill policy. The cache controller ensures that you don't put the same cache block into two or more ways, because that just causes all kinds of problems. So when a cache block is filled, we make sure that doesn't happen. So the idea is that one or none of these uh, of these um, ways will hit. Okay. So if one of them hits, we have a cache hit. If none of them hit, we have a cache miss. And then, depending on which one hits, that then controls our multiplexer. And so if the leftmost way hits, so if this tag compares but then these don't, okay, then we're going to grab this data and forward it onto the processor. Okay. Well, unfortunately, I'm out of time, so I'm actually a bit over time. So I think this is a good stopping point. So we'll pick back up here in a couple days. So I'll talk to you in a couple days. Hope everybody's healthy and happy.